This lecture is about the Perceptron learning rule and then leading into why we need something called backpropagation. Before we looked at simple networks that would just do some simple logic gates, but we had to predefine the weights. The learning rule is called the Perceptron learning rule. And it goes like this. If you want to train the connection going from neuron number J to neuron number I, this would be called Wij in a naming convention where Wij goes from neuron J to neuron I. Neuron J has an output Xj. Neuron I has an output Xi. And those are calculated just like we did before by summing up the inputs and applying the activation function. The Perceptron learning rule for updating that weight looks like this. Where Wij is the weight from J to I, Xj is the output from neuron J, and T sub I is the desired or target output for neuron I. And C is the learning rate. All right, so let's do this for the OR network, a real simple network. It has two input neurons. And an output neuron. And the threshold for that is 0.5, like we used before. So the weights that we're going to update are W31, this is neuron number 3, and W32. And they're both set to initial small values, 0.1 and 0.1. So the learning rule applied to each of the neuron weights And notice the difference between these two is the fact that one of them has an x2 and the other has an x1. So one of them trains the weight going from 1 to 3, and the other trains the weight going from 2 to 3. And we want to do the OR logic gate. And there are the training pairs, the inputs and then the target output. We're going to use a learning rate of 0.25, and we're going to cycle through these training pairs. We're going to make a big table, and in the table we're going to list the input neuron 1, which feeds straight through to output 1. Same thing for 2. The input goes straight to the output, and the target is going to be listed here. And then over here, we're going to calculate the net input for neuron 3. We're going to calculate the output for neuron 3. We're going to take the error, because we need that for the learning rule. And then we're going to calculate new weights based on the formula above. All right, so when we apply the 0, 0 input, our target is 0. And we process it. We take 0 times 0.1 plus 0 times 0.1 gives 0. The net input is that. And then the threshold is not exceeded, so the output is 0. And that's the answer that we wanted, so the error is 0. And then the weight updates, we take the current weight plus the learning rate times the error times the input x1. So that's the full formula. There is no error, and so the weight does not change. The same thing happens to 3, 2, so the weight there stays at 0.1. Then we apply the next set of inputs. We have 0 times 0.1 plus 1 times 0.1 gives us a net input of 0.1. It's below the threshold, so we get a 0 out. We wanted a 1, and so the error is 1 minus 0 is 1. And the weight update for this is going to be 0.1 plus 0.25. The error is 1. And the signal along the path from 1 to 2, that's I1, is 0. So that weight does not update. But this second one does, because both the error and the signal are 1. And so that's going to update to 0.35. Likewise, this set of inputs is going to yield 1 times 0.1 plus 1 times 0.35, because now the weight here is updated to 0.35. But we still have 0 times that, so 1 times 0.1 plus 0 times 0.35 gives us a 0.1, which is less than the threshold. The output is 0. The error is 1 because we wanted a 1. But notice now this weight will update. And let's keep going, so we'll go to the next training pair. Now we get a 1 times 0.35 plus a 1 times 0.35, we get a 0.7. That beats the threshold. The output neuron fires. We wanted a 1, we got a 1, so we end up with 0 error, and the weights stay the same because we didn't get any error. If you repeat this process again, by the way, this is called an epoch. One pass through the entire training set. So we put in the 0, 0. We want a 0. The weights are 0.35. We get a 0 net input of 0 output. The error is 0 because we wanted those values, and the weights don't change. Do the next training pair. We got 0 times 0.35, 1 times 0.35. Below the threshold, so the neuron does not fire, but we wanted a 1, so we have an error. This weight doesn't change because x1 is 0, but this weight does change because x2 is non-zero and we have an error. So same formula up here, we just take the new weight of 0.35 and add 0.25 to it. Keep going. This weight does change because the x1 value is 1 and there is an error. Now for this one we have 1 times 0.6 plus 1 times 0.6, so we beat the threshold, so that neuron fires. We wanted that to fire, so there is no error, so the weights stay the same. I'll leave it to you, but if you continue, so this was another epoch. If you do another epoch, the outputs are all correct, and the weights don't change. Both of these indicate that this is trained. All right, so what about the XOR network? Can we train it? So it looks like this. Remember, it has that extra neuron in the middle. And we have all of the connectivity weights. For example, this one is called W42. This one is called W41, and so on. This is W31, W32, and this one is W43. If we write the Perceptron learning rule for each of these, what do we get? So we do the Perceptron learning rule that was up here. This one here, and we apply it to each weight. So we have W41, All right, so let's look at each of these formulas. If we want to calculate these formulas, we have the input x1 and the input x2. We'll know what those values are when we calculate the forward values. We'll know, again, x1 and x2, and we'll calculate x3 and send that on to neuron 4 to calculate x4. So all that's good, because then we know x4. And we'll know x3 when we calculate those values. And we have a target for output 4 because it's the XOR value that we're wanting to get out of the network. But what's the target for neuron 3? It's not tied to the output XOR, but it does affect it. And in fact, that neuron is hidden from the inputs and the outputs. We called it a hidden neuron. And because we don't know, or we can't even calculate, a target for neuron 3 because it's hidden, the perceptron learning rule does not work. So we're stuck. So people gave up on trying to train multi-layer neurons that have hidden neurons until somebody invented a method called backpropagation. That allowed calculating the error of that hidden neuron. So the basic idea is the same as the perceptron. If the weights, you have wrong answers, then update the weights to fix the problem to make the output better. But the secret here, or the thing that enables this to work, is that calculation of the hidden neuron. We still learn from training pair data. In other words, for a more general network that has n inputs and some hidden neurons connected together and multiple outputs. So this is an expansion of what we've already talked about, but now we're talking about a general multi-layer perceptron. So it has M outputs, a hidden layer, connected all different kinds of ways. We'll have a set of inputs then in our data. There are n numbers there. And then there are targets. And we'll have data in pairs, just like we had before. So it works the same philosophy as we have inputs and target outputs for the network. And the steps for backprop is step 0. We initialize the weights to small values. And then we apply inputs and calculate all of the activation values, all of the outputs of all of the neurons, which means we calculate the outputs O1 through O sub m. And then we calculate output neurons, errors. So we take the target minus the output to get each output neuron having an error. And then we do a thing where we backprop, propagate the errors back to hidden neurons. And then we adjust the weights of all neurons based on those errors. And then, just like before, after we're done with that, we go back up here, grab another set of inputs, calculate the forward propagation, and keep going. The people that developed this, originally a guy named Paul Weirbus in 1974, created the basic idea. A guy named David Parker in about 1985 reinvented. And then two guys made it popular. They said, hey, we can use this for a lot of really cool stuff. In 1986, they wrote a textbook that talked about backpropagation. It's called Parallel and Distributed Processing. So let's talk a little bit about the details of backpropagation. So we'll go through the same steps. The first step is the forward propagation. And it processes exactly like we've been doing before. For the input neurons, you simply copy the input value to its output. And then for other neurons, we do the same thing. You calculate a net input. You take the signal coming along the path times the weight to get a new net input, and then you apply an activation function to that neuron. And then if it's an output layer, you'll map those outputs to the O's that are the actual outputs from the network. So that's the forward propagation. Then the back propagation, so the backward, error propagation, is done according to this formula. So for the output neurons, take the error, the target minus the output, and then we multiply by f prime of that activation function. This is the derivative of the activation function of neuron J, and these are the output neurons. And notice that we have to match the counting of the output neurons from 1 to m with their actual neuron number in the entire layer, or the entire network. Okay, so that's for the output neurons. And then for the hidden neurons, we use this formula. And we need to draw a picture to go along with this formula. We're calculating the error of neuron J, the delta for neuron J, and neuron J feeds out to a layer above it, and this is neuron number L. And down here we're calculating delta J, and up here we've already calculated delta L from the output layer above. So for the output layer, we know all the deltas for all of these neurons in the output layer. Notice this is WLJ. Goes from J to L, and that matches what we have in the summation here. And so if we look at this inside the bracket, this is a summation of all of the deltas that J feeds out to. Remember, we're going from J to L. So a weight from J to L grabs the delta of the neuron it's fed to, and it multiplies by the weight along the path, and then it goes to this neuron, and that's the summation. So this is the sum of deltas that J feeds out to. And that's key because remember we've already calculated the deltas for the output layer, and now we've moved back to a hidden layer. And so we look at the output layer and add up all the deltas, and then we multiply by the weight of the path connecting the two. There's a good reason for that. If, for example, this weight here were 0, then this error would not be caused by this neuron because the weight connecting the two is 0. And so that's why this proportional weight is in this part of the formula. So we do that for all the neurons, the output neurons and the hidden neurons, and then we update the weights. With a formula that will look very familiar. It looks just like the Perceptron learning rule. Notice that the weight from K to J is updated based on the error of that neuron that the weight goes to, and it's also proportional to the signal that goes along the path from the neuron. So again, draw a picture. Here's neuron K. Here's neuron J. This is WJK, And so we update W based on the error up here and the signal going along the path XK. All right, I'm going to send you to another video that's posted, that was previously recorded, and it shows you a bunch of examples of how backprop was used. So refer to the video assignments as to which video to watch next and what to look at.